This particular problem, our aim is to find out the first 6 natural frequencies as well as the mode shapes for this aeroplane wing. See here, it is a simple Cessna aeroplane, and we are going to consider this particular wing. And coming to the boundary conditions, see this particular one end of this wing is attached to the cockpit or say fuselage of this small aeroplane, and the other end is going to be free. And the material with which this particular aeroplane wing is made is titanium alloy, and our aim is to find out the first 6 natural frequencies and mode shapes using ANSYS Workbench. Analysis on the aeroplane wing. I have opened the ANSYS Workbench. In the ANSYS Workbench, I am going to go to Analysis Systems. In the Analysis Systems, I am going to select this model, and I am going to drag it and place it on the project schematic. So once I have dragged this modal analysis system and placed it on the schematic, now I need to specify the material. So what I am going to do is I am going to go to the engineering data, and once I open the engineering data, right now this particular wing is made up of titanium alloy, and I think this titanium alloy is a material that is already available in the engineering data library. So what I am going to do is I am going to, instead of adding a new material, I am going to go to the engineering data sources, and in the engineering data sources I am going to select the general materials library, and from the general materials library I will scroll up and down to find out this particular material. So here I have found out the titanium alloy. So now what I am going to do is I am going to add it to my present analysis. So I am going to press on this plus button. So if I just press on this plus button, see a book shape has appeared beside this titanium alloy. This represents that this particular material is now available for us for our present analysis. And once I have done this, I am going to close this engineering data. Then I am going to right click on the geometric cell, and then I am going to go to import geometry, then browse, and from the browse I am going to go for say aeroplane wings IGES, and I am going to press open. And once I have imported this particular part file, I am going to just double click on the model cell in order to open a mechanical. As I have told you, the mechanical is the module in which we are going to perform several types of analysis, such as the structural analysis, transient structural analysis, thermal analysis, modal analysis, even advanced dynamic analysis, electrical analysis, and other sorts of analysis are going to be performed inside ANSYS Workbench using the ANSYS mechanical module. Now see, once we got this particular model into our ANSYS mechanical, now what you need to do is you need to go to the geometry branch and expand this branch and select this particular solid body, and you need to change the material assignment from structural steel to titanium alloy. So once you have changed this one, I am going to generate mesh with the default settings. So I am going to right click and just say generate mesh. So generate mesh, and once I have generated the mesh, now what I am going to do is I am going to go to the models. Now what happens, see, if I go here into the environmental toolbar, what happens, see, lot of types of loads are not present. See, they are not visible. So what it does means is depending on the type of analysis you are going to perform using ANSYS mechanical, the availability of different loads and supports will be there. So here in supports you are going to go for fixed support, and you are going to select this particular face and going to say apply. And once you apply, see here it is showing that this particular face has fixed support applied to it. And now we in modal analysis or free vibration analysis, we don't have any loads to apply on the object. We have only the constraints that are to be applied to the object. So I have applied the required constraint. Now what I am going to do is I am going to the solution branch, and I am going to right click on the solution branch. I am going to press solve. So once I click on solve, it is going to find out the natural frequency values and also the mode shape values. So here once the solution is done, in the graphics window, see there are some bars that represent the value of the natural frequency, and there is a tabular data here which shows the mode number and which shows the frequency of vibration. So what it means is, in the mode 1 it is going to vibrate at a frequency of 106.23 and the units is in hertz. So what happens, so in the mode number 1 or in the fundamental mode, this wing is going to vibrate at a frequency of 106.23. that means if any working frequency is nearer to this 106.23, what happens, the natural frequency of the wing and that working frequency are going to coincide, and this may lead to the resonance phenomena, which leads to the ultimate failure of this particular wing. Likewise, in the mode 2 it is going to vibrate at 51105 Hz. Likewise, we have found out 6 modes and 6 different frequencies. Now what we need to do is, we need to select everything by pressing just select everything by pressing control, and then what you can do is, you can just right click on them and say create mode shape results. So with this, what you can do is, until now you have known what are the different frequencies at which this particular wing is going to vibrate, but by understanding the mode shapes you can predict in which way the vibration will occur at that particular frequency. For that purpose, I have selected this option and I am going to right click on the solution, say evaluate all results. So once I evaluate the all results, see if I click on the total deformation one, so what happens, there are some displacement values that are represented here. So remember one thing, whenever you perform a modal analysis or free vibration analysis, you get some deformation results. This doesn't mean anything. You should not be relying on these values. You should not ignore these particular values. You are only supposed to take care, you are supposed to take these values as the input and this shape as the input. Other than that, whatever the results that is going to be calculated in the modal analysis, you will need to ignore. So for now, what I am going to do is, I am going to animate the mode shape. See, if I animate the mode shape, what happens, so it is going up and down. From this, what can I understand? If there is a frequency of 106.23, this wing is going to vibrate in the up and down direction, or if we come to the global if we come to the reference of the global coordinate system, it is going to vibrate in the y-axis. Then coming to the natural frequency number 2, and I am going to play the animation. See what happens is, it is vibrating in the x direction. So what happens is, this is a one type of mode shape. Then coming to third one, see here what happens, instead of moving up and down or sideways, it is moving in the form of a wave. So what happens if at this particular frequency, this particular type of deformation will occur in the wing. Likewise, you can check for the fourth one. See, this is the twisting torsion mode. So until now we have this is the torsion mode of vibration, and you see here it is a mixed mode of vibration. We can call it as a mixed mode of vibration at fifth mode. Then sixth mode also there is some mixed mode. See here, in addition to this particular translation, it is also having some sort of bending and other sorts of things. So this is how you can perform modal analysis on objects by only applying constraints, and you can find out these frequencies and mode shapes in which the body is going to deform. Then once you have finished this one, what I am going to do is, I am going to stop the animation. I can just close this one and I can just save it like file, say save, and I am going to save it as modal wing. Sorry, first I need to just browse for the location where I want to save the files, and I will just save wing modal analysis. Okay, so once you have saved it, it will be saved in the default say file format of this ANSYS Workbench. You can also save it in the form of an archive by just clicking on file, say archive, and just browse for the location where you want to save the file, and then give the name of the file and you press save. So then it will ask me what are all the things that I need to archive. Then I am going to click these two options as well, and I am going to click on archive. So this is how you can save the ANSYS project in the form of a archive file. So this is very easy to send. If you save the file in the archive format, it is very easy to share it with other people. Then in the next lecture we are going to see how we can perform modal analysis on a Audi car bumper. Thank you. To perform a free vibration analysis of a Audi car bumper, and the material with which the Audi car bumper is prepared is carbon fiber composite material. And remember, this material we have taken only for representative purpose, and if you want to analyze composite materials, there is separate procedure and modules for analyzing composite materials inside ANSYS Workbench. So in this problem, what we are going to do is we are going to try to find out the first 5 natural frequencies and mode shapes of this Audi car bumper instead of default 6 natural frequencies. Then once we find out the first 5 natural frequencies and mode shapes, we then try to find out the frequencies of this Audi car bumper in a particular frequency range, let us say somewhere around 100 Hz to 1000 Hz. Perform modal analysis on a Audi car bumper, we are going to drag this modal analysis system onto the project schematic, and once I drag it to the project schematic, I am going to go to the engineering data. Here, as I told you, the bumper is made up of this carbon fiber composite. For that purpose, I am going to go to engineering data sources. In the engineering data sources, I need to browse to the composite materials library, as the carbon fiber is a part of a composite material library. Then I am going to select this epoxy unidirectional 395 prepreg, and I am going to add it to my current analysis. And once I have added it to my current analysis, I am going to just close this engineering data manager. Now I am going to import the geometry by right clicking and say import geometry, and browse. You see there will be a history of files which I have previously imported. So here I have previously imported Audi car bumper, so it is readily available here itself. So I am going to just select it instead of browsing for the file location. So I am going to select it from here, and once I have selected from here, it is going to get updated or imported. And now I am going to just double click on the model cell in order to open ANSYS mechanical module. So remember, in this Audi car bumper model we have taken, there are 2 types of bodies. One is a surface body, another one is a solid body. So for the surface body, as I have told you previously, we need to define some thickness in ANSYS mechanical. For that purpose, I am going to select this surface body, and I am going to give the thickness as a 10 mm in the details window. And as a part of a caution, even after importing this particular model, the computer itself, the software itself has shown a question mark beside it, so that we can know that some input is missing for that particular part. So now once we have defined the thickness, now what I am going to do is, here see there are 3 solid parts for which I am going to apply structural steel as a material, and then for this surface or the top part I am going to apply carbon fiber as my material. So as I have already selected this part, I am going to change the material assignment from structural steel to epoxy carbon, and then I am also going to select all of this by pressing Ctrl, and then I am going to change the assignment to structural steel. So by default, as the structural steel is the material, so I need not change the material right now. So once I am finished, see here the connections have been automatically generated. Here if we look physically also, everything is bonded through adhesives or weld, so we can leave the contact type to bonded, no problem, we don't have any problem. I am going to right click and say generate mesh. So there is a caution that if you are working with such type of hybrid models, you need to mesh very carefully. But for this particular problem, we are going to just generate the default mesh with the default mesh settings. It will take a little bit of time because it's a little bit bigger model, as well as it is a hybrid model. So it will take a little bit of time to mesh and complete all the parts, and due to the curvatures as well. So it has a lot of curvatures, so it has to see, it has to just complete every area. So now as the meshing is done, see, even with the default meshing you have got a very good mesh, but you see, as an experienced engineer you should be able to see whether the mesh is accurate enough or not. So once we have done this, we are going to go to the model tab and right click, say insert, go to the fixed support, and we are going to fix these two faces. I'm going to just zoom in. So in order to zoom in and zoom out, you need to move the scroll wheel, and in order to pan the model you need to press the control button down and then press the scroll wheel in order to pan the object. So once I've selected this, I'm going to press apply. Now we have applied the conditions, required conditions. Now what I'm going to do is I'm going to just go to the analysis settings. If I just directly solve the problem, what happens? I will get the first 6 natural frequencies or mode shapes, but I don't want the first 6 natural frequencies. I do want only the 5 natural frequencies. So if I get to the settings here, see here the first option is maximum modes to find. So I want, how it is asking us how many number of modes do you want the computer to find, whether it may be 6, it may be 10, it may be 20, it may be 30, it may be 40, or it may be even less. So for now what I'm going to do is I'm going to change it, decrease from 6 to 5 and press enter. Now what I'm going to do is I'm going to right click on the solution branch and I'm going to solve the problem. Now you can see that we are only going to get the natural frequencies, first 5 natural frequencies of this particular Audi car bumper. And remember, this number of natural frequencies to be is dependent on the further analysis for which you are going to take this model analysis as a reference. For example, let us say further you are going to perform some harmonic analysis, and there you need to find out some more than 11 or 12 frequencies. So you can just type in 12 instead of 6 here. So you see right now the solution is done and we have got only 5 modes. I can once again go to the analysis settings and I can just increase the number to whatever number I want, because as I've told you, if you are taking a system, a real world system has infinite number of natural frequencies. So I'm going to just give 45. So if you are going to increase the number of modes to find, the number of equations are going to be increased and the number of the solution time increases drastically. So I'm going to just right click and say solve, and it will take a, because as this is a simple model, so it can pretty easily solve the 45 modes within no time. And then you can see it has represented the 45 modes, first 45 modes. Then you can also just select every mode, right click. If you want to see how this particular bumper is deforming in the mode 6 only, you can just select that particular one and you can just right click and say create mode shape, and you can just click on evaluate all results. See, and now I'm going to animate. So what happens? See, it is the 6th mode where the frequency was around, I will just tell you from the information, frequency was around 122.93 hertz. This particular bumper is going to vibrate in such a fashion, Then, so instead of finding out a number of modes, what I am going to do is I am going to reduce it to 6 itself. So okay, then I am going to give a range. So between which range of frequencies do you want me to find? For example, let us say, as we have as I have explained the example of a motor and a centrifugal pump. So the frequency of operation is 60 hertz. So what I am going to do is I am going to take a range from say some 30 hertz to 90 hertz, and I want to try to find out the natural frequency between these two ranges only. So this could limit my search. For example, if I am just cluelessly searching for infinite number of say natural frequencies, I will be not able to do. So for that, in order to limit my search, I can give the limit search range. So I am going to press S instead of S, and I am going to type in range. So I am going to just type in from 600. I want to find out from 600 hertz to say some 800 hertz. So once I have given the frequency range, I can just right click and say solve, and once I click on solve, we are going to get the frequencies that are present only between this range of frequencies. If there are any other natural frequencies that are outside this range, this software will not be showing us all of these things. So here within this range there are 6 natural frequencies. They are 613, 640, 653 and 692 and 728. So this is how you can perform. You can request the software to search in between the limit range, or you can also request to find out more number of modes if you want. Then once you finish this one, you can just save it by just going to file, say save, and in the save you are just going to type in Audi car bumper modal analysis, and you are going to save. And in the next lecture we are going to see how we can perform pre-stressed modal analysis and find out the natural frequencies for a machine frame. Thank you. Particular problem, we will try to investigate the vibration characteristics of a machine frame, and this particular machine frame is made up of structural steel materials, and it has 8 holes. See, these are the 4 holes on this side and these are 4 holes on that side. We need to constrain using the cylindrical support by leaving the tangential direction as free, and in order we are also going to add standard earth gravity and a distributed mass of 250 kgs for performing the pre-stressed modal analysis, and we are going to find out the first 6 natural frequencies and mode shapes. Purpose of performing modal analysis, that to pre-stressed modal analysis on a frame, the first and foremost option we need to do is we need to first select static structural and drag it and place it on the project schematic. And once I drag it onto the project schematic, then I need to drag the modal analysis and I have to just drop it on the solutions cell here. So what happens, there will be the data that is coming from static structural will be shared with this modal analysis. So whatever the material properties we have given, whatever the geometry we are taking, whatever the meshing and other loads and boundary conditions we are taking, all of these things will be shared with this modal analysis system. Then again here whatever the solution we have created, this will become as a starting point to this particular modal analysis. So this is how you can join 2 or more different systems and perform a coupled analysis. So as this particular frame is made up of structural steel, we don't need to give a material explicitly. Then I am going to right click on the geometry and I am going to import geometry and go to browse, and then I am going to select the machine frame and I am going to open. So once I have done this, I can just double click on the modal cell in order to access this ANSYS mechanical to perform this pre-stressed modal analysis. And you can observe that previously when we have selected the standalone systems, our outline tree was having only that particular system, but here what happens, we are performing a coupled analysis. So our outline system, our outline tree is having the data from both structurals as well as the model. So first we need to perform static structural analysis, and once we solve this particular problem, we are going to do the model analysis. Then we go to the geometry. We can see there are a number of parts and we don't need to change the material, as by default the structural steel is the material that was applied. So then we need to right click on the mesh, we just generate the mesh with the default mesh. And once we generate this particular mesh, see, I need to select all of these holes individually to apply the support constraint or some constraint. That takes a lot of time, or otherwise if there are many features that you need to select in order to apply constraints or boundary conditions or say loads, you can make use of a feature known as the named selections feature. So I am going to use the automated tools present inside ANSYS mechanical to select the holes. So now what I am going to do is, see, I'm just going to zoom in, and then I'm going to just select this surface or this face. And once I select this face, instead of selecting the 8 holes manually, what I'm going to do is I'm going to right click on this, and now I have an option called create named selections. So I'm going to say create named selections. Now it will ask me what is the name of this selection. So I'm going to just type in 8 holes. 8 holes. So instead of selecting only single hole and afterwards adding all the 7 holes, what I can do is I can ask this particular option, see, apply geometry items of the same. So if I select this option and press size, what happens, what are all the other geometric features that are of the same size will be selected automatically by the software. Now what I am going to do is I just selected the size and I am going to press OK. So now once I press OK, there is another branch known as the named selections that appears here, and if I expand this, I have created a 8 holes section. You see here, instead I have selected only one face, but instead of one face it is showing 8 faces, because we have opted for automatic selection of other faces of the holes based upon the size constraint. This is one option how you can use named selections, or otherwise what you can do, you can just right click on the named selections and say insert named selection, and once you select this option, you can either manually select all the holes. See, I can manually select all the holes to create a named selection like this. So create a named selection like this. See, I can just select it manually. I need to select 8, and if I select 8, it will show me 8 faces. I have selected only 3 holes, so it is showing me 3 faces. And another option is, one thing you can do is you can just right click on the named selection, say insert, and create named selection. In the geometry scoping method, you can change it to worksheet. So if you change it to worksheet, see here, instead of the graph being displayed, a worksheet zone has appeared in ANSYS mechanical. Now what? So coming to this, you need to right click and say add row, and then you need to select the entity type, whether the entity you are going to select is a body entity or a face entity or a edge entity or some vertex entity, mesh entity or something else. Here my entity is the face entity, so I am going to select the face entity. And what is the criteria which the computer should be using to find all the similar faces? So I am going to set the criteria to radius, because what happens, the radius, the diameter of the hole is somewhere around 20 mm. So if I specify wherever there is a face with a 10 mm radius, you need to select all those faces. And then operator. Operator is nothing but if I give some value, is the criteria exactly equal to that value? Is the criteria of searching can be more than that value, can be lower than that value? You need to define through operators. Here I should be having equal, and then the units are in mm, and the units is 10. So see, I have clicked on 10 and press enter. So once I have entered this, I can say generate, and once I say generate, see here 8 faces of similar radius have been selected, and this is how you can also select named selections using automated tools inside ANSYS Mechanical. And once you done this, see, you are going to right click on the static structural, say insert, and then you are going to insert cylindrical support. In the cylindrical support here, instead of selecting geometry to apply the cylindrical support, you are going to select it from named selections. So you need to select named selections from here, and you need to select 8 holes. You need to select 8 holes. Then once you have selected this one, as I told you, we need to leave the tangential direction free. So you need to change it from fixed to free by selecting from the drop down menu. And once you have given the cylindrical support, now what you need to do is, there is a distributed load of 250 kgs. So this 250 kgs is a load, let us say it is a dead weight of the motor and the centrifugal pump that is based on this particular frame. So what I am going to do is, I am going to just go to the model tab. In the model tab, in the geometric tab, I have a option called distributed mass. So I am going to select this distributed mass, and I am going to select all these faces, so that the mass which we are applying is going to be distributed on these faces. So I have selected this and press apply, and I am going to give 250 kgs. So once I give the 250 kgs, we have entered the mass. Now what I need to do is I need to give the earth gravity. We need to take into account the earth gravity or the inertial load. For that purpose, I am going to go to the static structural, go to inertial, and select standard earth gravity. And in defining a standard earth gravity, see here, if I leave it to default, what happens? The earth gravity is going to act in the z direction. No, I want to act in the y direction, that too in the minus y direction. So what I need to do is, in the direction, I need to change it from minus z direction to minus y direction. So I have selected and changed it to minus y direction. So this is how you can apply standard earth gravity and cylindrical support. And once you have finished this one, you can just right click and say solve static structural. So once it is solved, then the stress stiffness matrix will be calculated, and that stiffness matrix will be used in the equation to perform this particular analysis. So coming to modal analysis, once you have finished this one, you can just right click and say solve, and see here in this particular option, pre-stress is showing static structure. So what happens is, we are going to import the loads from the static structure. It is denoting that particular thing. And once you have finished this one, you can just click on solution. You have some frequencies. You can just click on this frequencies. You can just right click and say create more shapes, and then you can just say evaluate all results, and you can just animate those results. See, now what we are going to do is, in the next lecture, we are going to perform a simple modal analysis on the frame, and then we try to compare these two results. So what are the frequencies that we obtain here? We are going to compare it with the normal vibration analysis or free vibration analysis of the frame in the next lecture. We are going to perform a simple modal analysis on the machine frame, and we are going to find out the 6 frequencies, and then we are going to compare the first 3 natural frequencies obtained from free vibration analysis with the first 3 natural frequencies obtained from the pre-stressed modal analysis. So for that, what I am going to do is, I am going to go to the analysis system and drag the model system into the project schematic. And once I dragged it, I am going to right click and I am going to import the geometry, and the geometry is machine frame geometry, and then I am going to double click on this particular model cell in order to open ANSYS Mechanical. And once I open ANSYS Mechanical, the first and foremost thing is I am going to create a named selection with all the holes selected. So here I am going to go to the mesh first, and I am going to just generate the mesh. And once I generate the mesh, I am going to just zoom in. I am just going to zoom in, and then I am going to select one face of the hole, and I am going to just right click on this, and I am going to say create named selections, and I want to apply geometry items of the same size, this selection to same size geometry items, and I am going to rename it as 8 holes, and I am going to press OK. So once I press OK, see here a named selection group has appeared in the outline tree with 8 holes. So it has 8 faces selected. Okay, then I am going to right click on the model and say insert and go to the cylindrical support, and in the cylindrical support, instead of scoping method from geometry select, I will change the scoping method from geometry selection to named selection, and I am going to select the 8 holes named selection option here. So once I selected this one, this particular boundary condition has been applied to all the 8 holes. But now what I need to do is, I need to free up this tangential direction motion. So what I'm going to do is, I'm going to set it to free instead of fixed. And once I've changed this one, I have given all the required constraints. So I'm going to right click on the solution and I'm going to solve. And now once I have solved the problem, you can see the first mode natural frequency is 33, whereas the first mode frequency in the pre-stressed modal analysis is 8.39. Likewise, the second modal frequency is 42 here, but there in pre-stressed modal analysis it was around 16.26, and then the third natural frequency here in the free vibration analysis is 68.336, but there in the pre-stressed modal analysis it was around 19.47. So there is a definite effect of pre-stressing on the natural frequencies and modes of vibration of a structure. Then again, I am going to say go to analysis settings, and then I am going to give a limit or range to search from, and I am going to press yes. And in this range, suppose for example if I have given 0 Hertz to some 22 Hertz, or sorry 200 Hertz, then if I press maximum modes to find 6, what happens in between this range, the software is going to find out just 6 modes. If there are more than 6 natural modes within this range also, it is not going to show. For example, I am going to set this settings, and I am going to solve. I am going to right click on it, and I am going to solve once again. And see now when I just go to the selection, even though there may be more number of modes that are lying between the given range of frequencies, as I have set the number of modes to find to 6, it is only showing frequencies up to 118. So if I just go to the analysis settings and I just change it to some 10, then rerun the analysis once again, say going to rerun the analysis once again. See here, if I go to the solution, see I have more than 10 modes here in the range between say 0 to 200. Maybe I can increase the number of modes as well. See here, from the analysis settings I may increase it to 15, and I can just rerun the analysis once more to just see whether this number of modes to find is going to exceed the 200 limit or not. If it exceeds the 200 limit, what happens? It is going to show only the number of modes that are available between our range. So if I go to the solution, see there are only 10 modes within the given range. If we have even given more number of modes to find, it will only show what are the number of modes that are present in between this range. So this is one option. And then again, if you want to just create a deformation plot for mode 4 and then mode 10, you just you can just select both of these particular modes and right click and say create mode shapes. Now see what happens, the name here is representing total deformation and total deformation 2. So first of all what I am going to do is I am going to right click on the solution and say evaluate all results, and once I evaluate all the results, see here you need to have a name to identify. From this name you cannot identify which mode it is related to. So for that purpose, in order to know which mode it is related to, you need to select the solution first, and then you come to the details window. In the definition it will show you what mode this particular deformation represents. So here this particular deformation value is representing mode number 4, and if you want the corresponding frequency, one thing is you can go to the tabular data and you can find the frequency from here, or otherwise what you can do is you can just come to the information tab and you can expand the information tab, and here also you are going to get the frequency of this particular mode. So this is how we can perform modal analysis inside ANSYS Workbench. In the next section we are going to see how to perform different types of thermal analysis starting from conduction, convection and radiation problems using ANSYS Workbench. Thank you.